So we did this find max and delete
So
max.
excuse me, sir.
Yeah.
Sir, in sorted array, whenever in insert function, whenever we want to insert, it will take O login, no sir, because in sorted array we can use rather than using ON.
No, no, no. You see, in ologin, you can find the place where to insert. But to actually insert it, you have to move all the elements, right?
Okay, sir.
That's where it takes order. So we did that. Then find max we were doing, and yeah, find max was order one. Delete max is what we were doing, and I think I explained the logic to you, and we finally said this will take order log n time. Right? There were some nice discussions about swaps, but yeah, this will be order log n time. That's where we were. Now tell me, what are your doubts before I start talking about insert function?
Sir, sir, yesterday in the swap discussion, sir, you have told that there are at most L plus one swaps.
Okay, can you all see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, Swaroop, do you want to log in again? Just check. It seems everyone else can see.
No, sir. Actually, it doesn't work even if I log in again.
Okay, let me reshare. Let's try. Can you see it now?
Yes, sir.
Okay. Okay, doubt, Jay.
Yes, sir. So I was talking, sir, that yesterday you told it was all at most L plus one swaps. Sir, which means we got the upper bound of number of swaps. Sir, is there any boundary for the lower cases also? I mean, at least,
Right. Right. What do you think will be the lower bound?
sir, I think it is L minus one.
Okay, fine. Just give me a second. I'm getting an urgent call. Just a second. You want a lower bound for this. So you are saying it possibly you need at least L minus 1.
Yes, sir.
Okay. Sure. So in L plus 1 is just a replace, not actually a swap. 1 is just replace. So you put in the in this position, you put the last element, right? And then we say there will be at most L swaps. You see, in heap, suppose you are saying all elements are distinct. See, in general, elements can be equal to each other. Right? So, in that case, you may have to just, you may just be at the, you may not have to swap at all. That may also happen, that some elements are similar. Right? But suppose you say all elements are distinct. All elements are distinct. All elements are distinct. So what would happen? You will take this value. So right? And this value, okay. Okay, what can we say about this value? So let's think. So I have the root node. Let's not see the values. So let's try to work out in general. And what we are saying, we will take is an arbitrary location. Oh no, not arbitrary. We will take the last one. So that can be an arbitrary, depending on till where it is filled. Let's say it is filled fully. It doesn't actually matter. Yeah. Let's say it is filled fully. Okay. And I take this value and I put it here. Now,
So the minimum should be 1, I think.
yeah, but one you may say, but you see, yeah, you may say one, but then you see the heap may have only 2 nodes. So then there is only like, if the heap has only 2 nodes, then you just delete max will be like this comes here. There is no other swap. Right? If heap has only 2 nodes. But in general, yes. So you put it here, fine, this is gone. Now what can you say? Of course, you have to find out the max of these two. Yes, and that you are certain, if these two elements exist, you are certain that the max of this is larger than the element that you put in the current heap I have drawn. Right? The max is larger than the root. You're sure, right? Because at least this will be larger. This is a parent. This will be larger, if not this. So max has to be larger than the root. It may happen that this is smaller. This can happen, right? This can be smaller than this. But this has to be larger. So that means at least one replacement. And suppose, so you can say that, okay, now we have to think what is the minimum swap. We will have to, what's the minimum swap we will have to. So for that to happen, if it goes via that route, it will have to do L minus 1 if it has to go through with this route. So that means you want to avoid this route. Yes. You want to possibly avoid this route. So then, let's say this element is larger. This element is larger. So that may happen. So this is larger than this. So you swap with this element. Okay. So I swap with this element. That's where this has gone now, and this has gone here. Now you see. Now what do you say about these two elements? These can be.
This can be lower than that the replaced one, sir.
Yeah, this can be lower, right? Very easily.
Yes, sir. So we can stop at one itself.
Yeah, at most one. I mean, one can be a lower bound. Yeah, you have to see that what we mean here is constant. It will take constant time, because if the heap has size 2, it will take only just change it to here. That's all. If it has much more size, it will take 1. So you can do it in constant steps. Lower bound, but yeah, we don't care so much about lower bounds. But yeah, just because you're asking, yeah, we saw this will take. This may take just 1 swap, and this may be fine. Is that okay, Jay?
Okay, sir. Yes, sir.
Sure. Okay. Now, do you want me to write a code for this? Delete max? Or you think you can write a code? Okay. No response means yes, you can write the code, right? Okay. Sure.
Sir, no, it would be helpful, sir, if you write the code.
Okay. Sure. Let's try. Okay, you may have to help me. Fine. So delete max. what is the input you will give?
No
The
input.
heap, no, heap, you will have to give input heap, right? Heap will be
Yes.
as an array, and you have to give the size of the heap. Size of the heap, that's all. So you give that input, heap and size. Okay, I may write a bit of pseudocode, but let's see. So how is heap? So heap is an array, right, of some max size, but you also know the size. So that means you know from index 1 to index size, you have the actual elements of the heap. Okay, and 0 is don't care, and size +1 onwards don't care. So that is the heap static an array. Okay. Fine. Now you have to do delete max. So what you will do? You will put the element at the last location to the first one. So you will say, okay, h1 is equal to h of size, and decrement the size. Fine. Now you have put that value. Now you have to check from the root up to the leaf node. Okay. So then you have to use a loop. So you have to have a root index. So the index of the node you are under consideration. So node index, let me write node index is equal to 1. Right, that's where your node is. Then you have a loop. I'm just writing while true. I may have to add some condition that we will see. While true, what you will do? Find the left and right child. Yes. So
Yes,
left
sir.
is 2 times, or maybe right ni. Ni would be easier. Ni is 1 node index. 2 times ni. Right is 2 times ni plus 1. Okay. Now you find the max. Okay. So max is, let's say, find the max index of this. Let me just write simply if, or I define max. Yeah, don't worry, I'm not writing int and all, so you can take care of it. So max is max of, no, I need the index, so better I should say if HL is greater than HR, max is L, max is the index that has the maximum value. Okay, you may use else, or you can simply write max is equal to, you can initialize max is equal to R, and then you can have this condition. That may work. Max is R, and if HL is greater than HR, max is L. So max just denotes the max, the child that stores the maximum value, storing max value.
Sir, both can be equal, sir, like two values of heap.
They may be equal. They may be equal. Then your max will be R. By default, you are choosing something.
Okay, sir.
Doesn't matter. Yeah. So fine. But here we will not worry too much about the equal cases. But yeah, they may be equal.
Sir, sir, we also have to take care that L and R both are less than size.
Very good point. Very good point. So then it may happen they may go beyond that size, right? So that means what have I missed? Okay. So you have to see. Right. So after this, we have to make a check. If L is less than N, size, no, L is greater than size. That means the node has no child.
Yes, sir.
Yes, sir.
L says just return Nothing to be done if L is greater than size. Okay. Otherwise, if, yeah, we can write like that. So now this case is done. So only thing that can happen, right. So what I can write, say max is equal to R if R is less than size, R is greater than size, then max is L. Okay. And then I will say, okay, else if HL is greater than HR, then max is L.
So if R greater than size, why should max be L if the value is it's like if the node itself has a smaller value than sir?
No, I'm finding the max among left and right.
Okay.
So one of them will have this, right? So max is L, otherwise max is R. Okay. Yeah. I think you have to also write an else. So okay. Done. So you found the max index. Okay. After you found the max index, you have to compare it with your with the current node Ni. So then you do this. If h of Ni is, if it is already larger than h of max, then return nothing to be done. Okay. Otherwise, so you will go here if you don't do this. So otherwise, what you will do, you have to swap.
Ni is equal to max.
You have to swap. You have to write a swap function, right? Swap function between, so you have to use a temporary thing and you have to use a temporary. So swap Ni and max, I'm just writing here, but that means you have to use 3 steps. You have to create a temporary variable, store one of the value and swap. Swap this. Okay.
Sir,
So,
swap Ni and max or H of Ni and H of max?
yeah, same thing. H
Okay.
Ni, H max. Okay, and then Ni becomes max, right? And you continue in your loop while true. I think I don't need any other condition. While true will work. Anybody find some serious flaw, and then we can see. Otherwise, I think this should work. You may make it more efficient, maybe, but yeah, this may work. Okay.
So why we are writing that else max equal to R? We have initialized max equal to R only at the beginning.
Okay. If I don't do that, this will still work, right?
Yes.
I don't finalize. Okay. Yeah, sure.
So why do you write if L greater than size then return?
Right. Yes. See, why do I write that? See, L is the left child. Yes. If the left child itself, the index is larger than size, that means the node does not have any children.
Understood.
Okay. That means nothing to be done. No. So you see this, you will keep on going into this loop, and wherever you find a condition where a node has no children, you will return. Or you find a condition where this happens. That, yeah, if the value at that node is larger than the max of the children, then also you will return. You will, that means the loop will be over. Otherwise, you will continue. And you see, one of this will happen because there will be some point where you will keep on, you are going down one point, you will have no children. That time you will return. Okay, so this should work. And complexity is of course order log n because you keep on going down, and the height is log n. Okay, are you happy with that? Then we can move to insert. Let's talk about insert. Now you know heap well. You can actually tell me how it will be done. So let me draw a heap and let me give you a note that you have to insert. So I'll use the same heap. 25, 30, 20. Okay. And suppose you have to insert 200. What will you do?
Sir, insert at first vacant position and keep moving up till you find a valid position.
No. First of all, you have to insert a node, right? You have to insert a node somewhere. Where will you insert?
Means the first vacant leaf.
Rightmost
Good.
of the lowest.
Remember?
H of
Lowest.
size.
Sure. Size plus 1. Remember, okay, again, I think Shivansh also write L size. Remember what we are doing? We are storing things from 1 to size. Okay. So H1 to H size will store the heap values. Okay. H0 is don't care. And size plus 1 onwards also don't care. Okay. So that's why I'm using up to size. And that's why it's checked L is greater than size. Now, here I will insert it size plus 1. Yes, I'll insert it here. That is size plus 1. So I put 200 here. Okay, at size plus 1 index. Why do I do that? Remember the thumb rule? Ensure the structure property. So it will ensure the structure is of the heap. Okay. Now you try to ensure the value property. So this ensures the structure property. Now you do something to ensure the value property. What will you do? That is very easy.
Check with the parent. If the parent is smaller, then swap.
Yeah. So this is easier. No comparison with the children. Check with the parent. Swap if parent value is smaller. That's all. That's all. And you keep on doing that until you reach the root. So keep going up. I mean, if you need to, until you reach the root. That's all. So in this case, what will happen next? You will compare this value with the parent. And of course, parent is smaller, so you will swap it. So you will get 100, 200, 25, left one remains as it is. Okay, and that's where your node is now. Now compare again with the parent, and you see your parent is smaller, so again swap. So finally, your heap will be 200, 100, 25, and the left one remains as it is. I think this one is much more easier. This one is much more easier. And the complexity, you have to go at most to the height of the tree. Height of the tree, that is log n. So complexity is order log n. Do you see any problem? Do you see any problem at all?
Sir, we can't keep on doing insert operations. Means there is an upper limit of size in a way.
That's okay. So you may be given in the problem that what is the max size you can assume, number of elements. You may initialize with that maximum size. Yeah. Yeah, I understand your point. Yeah, you cannot do it infinitely. But yeah, there are ways you can, means up to whatever you can support, there are ways you can do it. Of course, if the heap cannot fit in your memory, that's a altogether different issue. So now, okay, do you want me to write the code? Then we can do that together. Insert heap. What are the things you need? What are the things you need as input?
Heap
Sir,
size and
array
value.
size.
Heap, size, and the value. Okay, let's write quickly. H of size plus 1 becomes new val. Good. Now you have to compare, and so you have to use a loop. And you have to create that ni. Ni is size plus 1. And of course, you can increment the size also. I don't know if you need it, but I think better to increment the size. Fine. Insert done. Now you have to percolate up. So again, a while loop. Let me use true, or we will see if you need some condition. While true. So you will stop whenever you are at the root. So if ni is equal to 1, you return yes, and then you compare it with the parent. So what is the parent? So parent is ni by 2. Yes. So p is ni by 2. If HP is already larger than h of ni, then also you return. If it doesn't happen, you swap HP and HNI, and NI becomes P. Will this work? I just followed the previous logic. Did I miss something?
But if P becomes 0, then we've reached the top.
No, see, first of all, that's why we are doing. If Ni is equal to 1, you return. So
Okay.
that means Ni will, yeah, P will be greater than 1 always. Okay, so that should work. And this is order logging.
Sir, we can also do HP greater equal to HNI.
You can. I will see you can. Sure. Okay, so this was easier. After we did the first one, this was easier. Good. So we have. So are we done with the heaps? We have done find max. We have done delete max, and then we did insert. Are we done with the heap? Anything else remaining?
Sir, how to delete a particular element, sir?
You see, each ADT has a specific purpose.
Okay.
Okay, so heap is not meant for deleting an arbitrary. Okay, let me ask you, what is the complexity of searching an element in heap? Complexity of searching an element in the heap.
Order n.
Anybody can do it better than order n? No, can't do better than order n. Because there is no sorting involved, right? So where will you find that element? How will you start searching for an element, right? So yeah, so you have to, in the worst case, you may have to search all the elements. So that is why if you have to do search, heap is not a good ADT. So you have to ensure what are the operations you need.
Maintain a pointer to each element. Means if the elements are of normal size, you can maintain a pointer array. Is that possible?
No. But you see, you may have to search for an element, an arbitrary element. Does it exist in the heap? What will you do then? Yeah, I understand what you're saying, like what we did in disjoint sets, that for each one that is there in the heap, you can have a pointer. That's fine. That's all right. But I'm saying in general, it's not good for search. But suppose you are saying, oh, I have to delete an arbitrary element. if I have a direct access to it, like what Gaurav said, then you can verify that you will take only order login time if you have a direct access to this. Okay, I will leave it as an exercise for you. This is actually part of the problems I'll give you for heaps. It's very easy, but you think it will take only order login time if you have a direct access to that element. Okay, but yeah, searching is not easy in heaps. And yeah, that is not an operation that heaps are meant for. You talk about these three operations. But are you not able to think of anything else important for heaps? How will you create a heap? How will you create a heap? Think about the scenario. How will you create the heap? There are two scenarios. You get all the elements one by one. And scenario 2, all elements are given to you in any arbitrary order. What will you do in scenario 1?
So repeatedly call insert operation.
Yeah. So keep on inserting one by one. What is the complexity of creating a heap in this way?
Sir, n log n.
N log n.
And log n. So you see, when the size is 1, it will take log of size, right? So it will be summation over log m is equal to 1 to n, right? And that you can see this is order n log n. This is order n log n. Yeah, this would be order n log n because this is log of n factorial. This is log of n factorial, right? Log of m plus 1 plus log of 2 plus log of 3 up to log of n, log of n factorial. And this is less than equal to log of n to the power n less than equal to n log n. This is O log n, O n log n. Anybody feels, oh, this is not a good bound, I can do better than n log n for this? Can one also prove a lower bound on this? Lower bound is also n log n. This is an upper bound. Lower bound is also n log n. How will you do that? Upper bound. What about the lower bound? Simple trick. What will you do?
Sir, the given summation is less than or equal to summation, greater than or equal to summation over m from n by 2 to n log of n by 2.
So you will take only from log of n by 2 plus 1 to n. Right? Multiplication of that. And that is greater than equal to log of n by 2 to the power n by 2. Yes, and that will give you order omega n log n. So if you take only the n by 2 elements, you can prove this is omega n log n. If you take all the elements, you can prove this is order n log n. So this is a type bound. Yes, you can also say theta n log n for this. So if you keep on inserting one by one, you cannot do better than n log n. That's what I want to say. Yes, but you can do it n log n. You will not take worse than that, but you cannot do better than that. Now, why am I writing a scenario 2? Can I do better than this in scenario 2? So here all elements are given to you already. Can you do better than this? What do you think? All elements are given to you. What is your feeling? Do you think you can do better than n log n? I'm just taking an example. Yeah, I'll take a heap in the reverse order, and we will take that example. Oh, don't sort. But anyway, if you sort, how will it help you create the heap?
Sir, if we sort in descending order, so we can easily just insert the elements. Like that would itself be a heap, that array.
Sure. Yeah, sure. I agree. I agree with you. If you sort it, yes, it's also a heap. Yeah, because the values are decreasing, so parent will always be larger than the children. Yes, but it will take n log n, as you have said yourself. Okay. So no, that's not the case. So let's see what you can do. So I'm giving you some elements. So scenario 2. 20, 25, just in the reverse order. 30, 50, 100. 5 elements are given to you. You have to build a heap out of that. They are given to you together, not one by one. Okay? What will you do? Tell me first thing. Now you know sufficient. What will you do? First step should be easy.
So first step, we have to take max element and put it in A1.
No. That's why I said, remember my thumb rule, then you tell. If you do max, you will take order n already.
Some middle element.
Thumb rule. I talked about the thumb rule. Ensure the structure property, then ensure the value property. How will you ensure the structure property? This is already a heap that follows the structure, right? This element is nothing.
Inserting everything in an array.
Yeah, just assume this is a heap. I mean, this make it as your initial heap that follows the structure. So that means your heap is this 20, 25, 30, 50, 100. Yeah, it's a proper min heap, but I want to create a max heap. Okay, I want to create a max heap. So this is not correct, but it follows the structure property. Follows the structure. Restriction. Okay, now I have to just do some changes of values so that it starts following the value restrictions. Okay, now do something to follow value restrictions. What is that something you can do? Now let's observe this. Okay, so we will do something bottom up. Let's do bottom up. Let's go from the last leaf. Is it a heap? Is this node a heap?
Yes, sir.
Yes, sir.
All leaf nodes are heaps?
Yes, sir.
Yes, sir.
Okay, very good. So we know all leaf nodes are heaps. Okay, how do I know what is the last leaf node? Or say, what is the last index of an element that has a child?
Size by 2.
Size by 2.
Size by 2. That will find a parent, right? Okay. And after that, no node has a parent. So size by 2 is the last index with a child. After size by 2 index, you cannot have a child. Because, size by 2. Because you found the child of the last one by size by 2. That's all. And this cannot have a child. So that means size by 2 plus 1 up to size are already heaps. Now what you have to do, you have to go backward. Now go from size by 2 up to 1 and ensure that the subtree rooted at each index becomes a heap. So go from size by 2 to 1 and at each index ensure that the subtree rooted at that index is a heap. I mean, you do something so that this is ensured. And keep on doing it from size by 2 to 1 and you are done. Wow, that's all. That's all. Okay. What do I mean by this? Okay, I'll first show you the example and then we will talk about this more. So what I'm saying, so here size is 1, 2, 3, 1, 2, 3, 4, 5. Size by 2 becomes 2. So yes, this is the index of the last node with the children, or a child. So these are already heaps. Now what I'm saying, you start from here, then you go here and ensure that they become heap one by one. How will it help? So let's take an arbitrary thing like this. Suppose this is I. What I'm saying, it will have a left and right subtree and both of them are heaps. Yes or no?
Yes, sir.
Both of them are heap. Now this node may violate heap property. So what I'm saying, okay, now I have to ensure that the heap property is followed. They are already heaps. Now make this a heap. That's all I'm doing at this index. Now when I'm going to this index, what I'm ensuring, because I'm going bottom up, this is a heap, this is a heap. Now this may violate heap property. You do something so that this overall becomes a heap. That's all. So at an arbitrary index I, so at index I, what you are saying, this has a left and right subtree and they are heaps. This is a heap and this is a heap. Now AI or HI may violate heap property, not value property. So do something, you can tell me what is that something, so that the subtree rooted at I becomes a heap. Now, whatever we have covered, you can tell me now, what is that something you can do?
So like we did that in delete.
Very good, very good. That something is nothing but, that is just analogous to delete max. Now you remember delete max, what we did? Delete max, we took the last element, you put it to the root, and we say, okay, this is a heap, this is a heap. Now this may violate heap property, so I have to do something. So I just compared it with the max of the children, do swap, keep on doing swap until we go to the leaf node. That's all. So you do something analogous to delete max. So that means the code will be for I is equal to size by 2, I should be, I need to go up to the root, right? So I should be greater than equal to 1. I minus 1. For this loop, you have to write some function. I call it max simplify. That is very similar to delete max. What do you need to give? The heap, the size is there. Yeah. Yeah, this will depend whether what you are storing inside this structure, but say size and I. That's all. That's all you have to give. Okay. And max CP5 will be similar to delete max. Only change will be you don't decrement the size and you start with I rather than starting from the root. That's all.
Sir,
Hmm.
sir, for different for different I, there would be different sizes for that particular heap. Means I and its subtrees.
No, no.
So sir, so size would be different for all. So how we are how we will find that
No,
size from this
I'm
size?
talking about the original size. I don't change
Yes,
the
sir.
size.
So sir, in delete max we need size.
Yes, so this is the size. You see, you don't have to delete anything, right? You needed size there. One important thing was you need to delete. But here you don't have to delete anything. What you are saying now, what will be max CP5? Max CP5 H size I, right? So in delete max, you started deleting something. You don't have to delete anything. Now you start with your node index is equal to I. Okay, and do everything else while true.
And sir, when we will terminate it?
While true, same thing. You can terminate at two.
Like how we will reach end means end of the subtree.
See, it's the same thing, right? So you're starting from I. There are two conditions for termination. One is you reach a leaf node.
Yes, sir.
Reach a
So,
leaf
sir,
node.
how we will check that, sir? Reach a leaf node.
Why not? You will just check if same thing. If L,
Okay. Yes, sir.
if L is
Yes, sir. It would be greater than size. Yes, sir.
Check.
Yes, sir. Got it.
So this will be very similar. This is actually the same function you can write after changing this n equal to I. The same function of delete max. You can just copy things from there to here. Okay. So, okay, anybody else has a problem that, yeah, I can just follow whatever I did in delete max here, except that actually deleting something. I percolate from the node to the leaf at most.
Sir, the leaf node, sir, how we identify it?
Right. Okay, let me try. So what we will do? N is equal to I, right? So what is the left node? L is 2 times Ni, and R is 2 times Ni plus 1. Then you say if L is greater than size, then return. Nothing to be done. If L is greater than size, that means your node is a leaf node.
Sir, but that is true for the prime tree. I mean, the biggest tree. Is it also true for subtrees?
No, what do you mean by subtree? I'm not using anything about subtree. I'm just taking it as a part of the tree. You see, this loop was valid in recursion. So you would have gone one step down, you would still use the same loop, right? Again. So why can't I start it from some arbitrary I? Size is not changing, size is given to you.
Yes, sir, I understood.
Then you find the max and swap, right? And second condition is if the value is larger than the max, then also you return. So max CP5 very similar to delete max. Okay. Now we understood how it works. So what is the complexity we will get? This is what is the complexity we will get? Omega what?
Sir, order size.
Order size. We will get order size. Order size. If they are an element, that means order n. Wow, we love order n.
Sir, how?
Yeah, that's the question. How? So yeah, how? Because it looks like, oh, each max heap will take log n time, and you are doing it for roughly n by 2 times. It should be n log n, isn't it? It looks like n log n.
But sir, we are checking only for size by 2 number of parents, and we are making only constant number of swaps.
No, swaps are not constant. Swaps are not constant. Swaps can
Means
be of
like
the order of
for
size.
parent having index size by 2, we are only making one swap and then going to the parent of size by 2.
Right. But size can be really large. Right? Can be really large, and then you can have order log n swaps sometime.
Sir, can you please scroll down? Sir, where have you used swap function?
I did not write. I said you just follow things from the reference.
Okay, sir. Okay.
The same thing. If you want me to write, I can write again with your help. But yeah, same thing. Okay. So
So,
now, yeah.
so basically we are doing one swap for size by 4 elements and 2 swaps for size by 8 elements and so on.
Very good. Very good. So actually, yeah, this is the idea. The idea is that as you keep on going up, you have to do more swaps. But then the number of elements are also small. Okay. So this is how you can get the idea. So when you are here, at this label, you need say only one swap, because you go from that node to down. Yes. At this label, you need only 2. And here you need 3, and so on. Let's say up to L. At label L, you may need L swaps. But you see what is happening as you go up, the number of elements are decreasing by half. Yes, the number of elements are decreasing by half. So, yeah. So you can see it's very simple. You can see this very simple. If there are n elements, so here we will have n by 2 here, roughly, n by 4 here. Okay, let's do it. Suppose there are n is 2 to the power L plus 1. Okay, let's take the simple case. So then at label 0, I have one element. Label 1, I have 2. Label L0, L1, L2 have 2 square. L is equal to L, bad notation, but yeah, 2 to the power L elements. Okay, and 2 to the power L is nothing but n by 2. Yes, so this is n by 2 to the power L. Yeah. Plus 1 maybe. Yeah, plus 1. So you see what is happening? At label 0, you have n by 2 to the power L plus 1 elements. At label L, you have 2 to the power L elements. So how many swaps you are doing? At label 1, you are doing L swaps. So L times n by 2 to the power L plus 1 plus L minus 1 times n by 2 to the power L plus so on, and yeah, something like that.
Sir, how is the number of elements n upon 2 power L plus 1?
Sure. Let me do it very clean way. I just wanted to give an intuition, but I'll do it in a very clean way so that you can follow this. Okay. So we will do it to a solid 10. You may have a class, so we will do it tomorrow to be continued. I'll do it in a very clean way so that you can follow. Right now, I just wanted to give intuition, but yeah. Sure. So we will see how build heap will take only order and time. Okay, that is due for tomorrow. Okay, anything else? Otherwise, we can stop now and continue from here tomorrow.
Thank you, sir.
Okay, thanks. Thanks.
Thank you, sir.